Hello everyone, this is Prashanth. Let's continue with the last lecture. So in last lecture, just I have completed about regarding UART. UART, Universal Asynchronous Serial Receiver Transmitter Communication Protocol, along with SPI, Serial Programming Interface. So these are the two communication protocols I completed in the last lecture. Along with that, what are the main structure of UART? What are the advantages? What are the disadvantages? What are the use cases? That are the use cases applied in IoT for both UART and serial communication protocol that completed in the last lecture. So now I am going to entering into the another communication protocol, that is I2C or IAC, Inter Integrated Circuit Communication Protocol. It is very useful to connecting the IoT device through the communication protocol in the world. So here, what is I2C or IAC? Simply inter-integrated circuit. IAC stands for I2C or IAC, inter-integrated circuit communication protocol. It is multi-master serial communication bus for connecting low-speed devices. So it is very important. The previous serial communication serial programming interface communication protocol, it is only single master, different slaves. So here, inter-integrated circuit communication protocol, multi-master serial communication bus for low-speed devices. So here, multi-master architecture of I2C, unlike SPI, I2C supports a multi-master architecture. It means multiple devices can initiate communication on the bus. That is the main aim of I2C. However, only one master can control bus at a time. One master bus at a time. So that is the only one master can control the bus at a time. So that is the what is the bus arbitration here? If multiple masters attempt to start a communication simultaneously, a bus arbitration process takes place. Typically, the master with lowest address or fastest rise on the SDA line wins the control. So this is the actual process will going on the inter-integrated circuit communication protocol. That is the very important. Next one, what are the addressing modes of addressing data of IAC, inter-integrated circuit communication protocol? Each I2C devices has a unique 7-bit address, allowing multiple devices to share the same bus. The master sends the devices address to a part of the communication start sequence. Address format and address scheme. The address includes 7-bit devices, address and read write bit to 7-bit device, address, read or write bit. And addressing schemes, the master can transmit the address followed by a read or write bit. The address slave acknowledges the address by pulling the SDA lines and slow. Next, data transfer by using here I2C, it is a half duplex, but SPI supports full duplex communication. But I2C supports half duplex communication. Half duplex communication. So meaning data can be transmitted one direction at a time. That is okay. Start condition, address space, data transfer, and stop condition. So here the start condition initiates communication by pulling SDA lines. Low SEL is high. The addressing phase, the master sends a 7-bit slave address followed by a read or write bit. Data transfer, the data transfer is nothing but the master or slave transmit data 1 byte at a time with an acknowledgement bit after each byte. The stop condition, it terminates the communication by releasing the SDA lines with the SEL is high. That is the stop condition. What are the key points here? The key point I2C is suitable for connecting multiple low speed devices on a shared bus. The multi-master capability provides flexibility in system domain. That is okay. Addressing scheme enables communication with specific devices. Data transfer is synchronized using the SCL clock. So that these are the key points regarding I2C communication protocol. Next one, advantage and disadvantage over UART and SPI. So compulsory UART, SPI and I2C. Just we need to compare advantage and disadvantage of among these three. That is the essential thing here. So the same I2C versus UART here. Advantage of I2C over UART, supports multiple devices. That is okay. Requires fewer lines. It requires very few lines to communicate the data. Built-in addressing for devices often includes pull-up register for simpler wiring. Disadvantages of I2C over UART, lower data transfer rate, more complex protocol with stop or stop condition acknowledgement, susceptibility to noise due to the shared bus. So these are the some disadvantages over the I2C over UART. And one I2C over SPI, previous I2C over UART, here I2C over SPI, supports multiple devices on a single bus, requires very lines and simple wiring and addressing same as like UART. So the disadvantage of I2C also having some disadvantage compared with SPI, lower data transfer in communication complex protocol with start and stop condition acknowledgement susceptibility to noise due to the shared bus, same as like UART only. So these are the some advantages compared with I2C, compared with the advantage and disadvantage compared with the UART and serial programming interface. So in summary about I2C offers some advantage in terms of simplicity, wire count, multiple device support compared to both UART and SPI. However, it comes at the cost of lower data transfer speed, potential performance limitations. The choice between I2C, UART, and spends depends on the specific requirements of the IoT application, such as the data rate, number of devices, desired level of complexity. So these are the summary regarding inter-integrated circuit communication protocol. Next one, use cases. What are the use cases of I2C in IoT? That is just applied in on IoT devices. So here it is versatile protocol commonly used in IoT application due to the simplicity, ability to connect to multiple devices on a shared bus. So compulsory IoT is a one world. IoT world, Internet of things, nothing but compulsory every device connected to the internet. After for that, the one network we have to connect more devices. That just you can in our local language. So simplicity, ability to connect to multiple devices on a shared bus. So that is the very important. Here some use cases in terms of sensor network, in terms of actuator control. So in sensor networks, connecting multiple sensors devices. I2C is ideal for connecting various LED sensors like temperature, humidity, light, and pressure sensor to a microcontroller. And low power consumption, its efficiency makes it suitable for battery powered sensor modes. Actuator control, controlling multiple actuators. I2C can be used to control LED, motors and other actuators in a coordinated manner. The power management interfacing with power management ICs for battery charging and power distribution. So these are the some use cases regarding in terms of sensor networks and actuator control. And display interfaces and data acquisition system also some use cases here. In terms of data interfaces, connecting small displays and touch screen controllers also just we may use IoT devices. I2C is often used to drive LEDR orthogonal light emitting diode and touch screen controller interfacing with touch screen controller for user input. Data acquisition system, controlling data from multiple sources, Data aggregation also just we may use. Combining data from different sensors for analysis and processing. I2C can be used to gather data from various sensors and peripherals simultaneously. So these are the two use cases in terms of display interfaces and data acquisition systems. So these are the some applications of I2C in real-time clock, EEPRAM, electrical erasable programmable read-only memory and memory devices, audio codes. So for in real-time clocks, interfacing with RTC for timekeeping and calendar functions also just we may use. Storing configuration data or calibration parameters also just we may use, and audio codes interfacing with audio codes for audio processing. And some key benefits of I2C in these applications include reduced wiring, multiple device support, and low power consumption, and simplicity, relatively easy to implement and use case. So these are the some key benefits in I2C in these applications include reduced wiring, multiple device support, low power consumption, and simplicity. Next one, comparison of interfaces along with features here in terms of data transfer, clocking, data rate, number of wires, topology, addressing, complexity, and use cases. So these are the features among UART, SPI, and I2C. In UART, serial, asynchronous communication protocol, synchronous and synchronous communication protocol. Asynchronous is UART. Synchronous is SPI and I2C. Just you remember for these two keywords. Data rate low in UART, medium in SPI, and low I2C. And the number of wires in 2 in UART, 3 to 4 and 2. Point-to-point topology, master slave and master slave. Addressing not required, required in I2C communication protocol. Complexity is low in UART, SPI medium, I2C is medium. Complexity is high, just we not able to use for developing any application. So compulsory maintain low or medium. That is the enough. And use cases: low speed communication and debugging, high speed data transfer and peripheral devices controlling system, and low sensor networks and low speed peripheral devices. So these are the comparison of among these three UART, SPI, and I2C communication problem in terms of different features like data transfer, clock rate to data rate, number of wires which required, topology, which type of topology it can use to send the data from one device to another device, addressing mode, complexity, and use cases. Nothing but applications. Next one, some key observations on I2C communication protocol here. In terms of data transfer, clocking, data rate, number of wires, and topology. Which just is nothing but features. Just we discussed in the last slide only. In terms of data transfer, all these protocols transfer data serially, bit by bit. That is okay. And clocking, UART is asynchronous, meaning it does not rely on a shared clock signal. SPI and I2C are synchronous using a clock signal for timing. And data rate, SPI generally offers the highest data rate, followed by I2C and then UART. Number of wires, UART requires 2 wires, SPI typically uses 3 or 4, and I2C only needs 2. Topology, UART is a point-to-point communication, SPI is a master slave, I2C supports a multi-master architecture having. So these are the some key observations of I2C communication in terms of data transfer, clocking, data rate, number of wires, and topology. So, along with that, addressing complexity use cases of I2C communication protocol and additional nodes. In terms of address, I2C it's the only one protocol that requires addressing for device on the bus. Very important term you to remember. And complexity, UART is generally considered for both simplest and followed by SPI, then I2C. In terms of use cases, it is used for the low speed communication debugging. SPI is well suited for high speed. I2C is commonly used in sensor networks and for connecting low speed peripherals. high speed data transfer. Then next UART. UART is for low speed communication and debugging So these are the some use cases of among three. Additionally, the table provides a general overview and there can be variations in specific implementations, just like next slide. So here the common applications requirements here when just use cases use cases comparison of use cases in among these three future the UART, SP and I2C in terms of data rate, number of devices, complexity, wiring and use cases. So the data rate low, high, medium, number of devices to multiple. So multiple. That's why it is used to develop some real-time applications in IoT. Low, medium, wiring simple, moderate and simple. Use cases for debugging. Just now only discussed debugging, low speed communication and high speed peripheral and display, sensor networks and low speed peripherals. So these are the common application requirements of use cases. Just comparison. Choosing the right interface for an IoT application is crucial for optimal performance, cost effectiveness and system reliability for efficient of data transfer. Okay, next one some you are ideal for some example for ideal for low data transfer. Just comparison point to point communication, debugging and logging and long distance communication. Examples: connecting a microcontroller to GPS module, interfacing with the GSM modem, sending sensor data to a gateway. For SPI, ideal for these three: high speed data transfer between the master and multiple slaves, controlling peripheral like analog to digital converter or digital to analog converter displays, and interfacing with memory devices. Application require process timings. Examples: acquiring data from high speed sensors, driving on orthogonal light emitting diode display, and communicating with the flash memory chip. Next, I2C, ideal for connecting multiple low speed devices on a shared bus. That is okay. Sensor networks and power management. Just it consumes low power and addressable devices. Compulsory every device having one addressing mode in order to do the proper functionality. And examples: connecting temperature, humidity, and light sensors, controlling LED and other actuators, interfacing with real-time clocks. So these are the some comparisons of UART, SPI, and I2C. So installation consideration, some small topic here in terms of factors to consider when placing and powering IoT device, including environmental conditions and security that will also be maintained. Device monitoring and placement condition. The first one, installation conditioners. Just we have to maintain one point by point device mounting and placement. Device mounting and placement are critical aspects of IoT installation that significantly impact device performance, data accuracy, and overall system reliability. Factors to consider: device type and function, sensors, actuators, and gateways. What are the sensors? Placement should optimize data collection, temperature sensors away from heat sources. Actuators, location should facilitate effective control. Gateway should be centrally located for optimal network storage. Second one, in terms of environmental condition, physical constraints, aesthetics, and accessibility. Environmental conditions in terms of temperature, humidity, dust, and electromagnetic interface. That also we maintain. Avoid extreme temperature that might affect device performance. Consider moisture resistance if necessary. Protect devices from contaminants that can be interfaced with the operation. place devices away from source of EMI, prevent data accident. Just you can keep away from the electromagnetic signals like that. It can harmful the device of some cases. Physical constraint, space availability, whether it is space or availability or not. Surface type, ensure compatibility between the device and the mounting surface, and weight and load capacity. Select appropriate mounting hardware to support the device's weight. And aesthetics, visibility and integration. Consider the device's visibility based on its function, that is hidden sensors versus visible sensors. Displays integration, ensure the devices blends seamlessly with the environment condition also, just we can monitor. And accessibility, in terms of accessibility, just we have to maintenance and user interaction. Consider easy access for repairs or replacements. Place devices where users can easily interact with them. Next one, mounting options. We have some mounting options here. Wall mounting, ceiling mounting, pole mounting. So these were IoT, purpose of IoT only. Wall, ceiling, pole, surface, enclosure mounting. Different mountings are wall mounting, suitable for indoor environments. Ceiling, it's ideal for sensors or devices that require the unobstructed view. And pole, used for outdoor applications or elevated positions. And surface mounting, for flat surfaces like tables or slaves. And enclosed mounting, protect devices from harsh environment. So these are the placement considerations. Sensor placements, optimize sensor location for accurate data collection. Avoid obstructing our interfaces and consider the orientation of field of view. So these are the mounting options is very important. Wall mounting, seal mounting, pole mounting, surface mounting, and enclosed mounting. Protect device from harsh environment. So in some cases the environment also it is not supposed to do the devices. At that case it can easily indicate the damages. So that can protected by the ensuring mounting. So these are the sensor placements. Optimize sensor location for accurate data collection. Avoid obstruction or interfaces. Consider sensor orientation and field of view. Next to placement considerations. Placement considerations, here sensor placement and actuator placements, gateway placement. In actuator placements, ensure proper alignment, minimize mechanical stress on the actuator, and consider safety and accessibility. So these are the factors in order to maintain. Otherwise, the device will get easily damaged. So the device will get damaged is compulsory. Data will also collapse. Gateway, in terms of gateway, maximize network coverage and signal strength. So in order to do the payments of on POS devices or any other transaction, compulsory we need to coverage and signal strength also should be very high. Avoid interference from the obstacle. So just you can avoid. Ensure power supply availability, whether the power areas are not, power is available or not, just you can check before that installation of the devices. So these are the placement considerations under actuator placement and gateway placement. By carefully considering these two factors, you can optimize this performance, extend device lifespan, and enhance the overall efficiency of your IoT system. Next one, power supply options in installation conditions. Considerations is one of the important factor. Selecting the appropriate power supply is crucial for the unsuccessful operation and longevity of IoT device. The choice of power source depends on various factors such as device type, environment, and desired lifespan. So it is very important. Device type, environment, desired lifespan. So in terms of power supplies, battery powered, primary batteries, secondary batteries, and consideration. Primary non-rechargeable, ideal for short-term disposal applications, that is lithium coin cell alkaline, like that. Secondary, rechargeable batteries suitable for long term operation, lithium ion, nickel metal hybrid, right now we are using. And consideration, battery life, charging infrastructure, environmental conditions and safety. So these are the battery powered consideration. Next, power supply, line power and energy harvesting also. AC power, DC power and consideration. AC power, alternating current directly connected to the main power supply. DC power, industrial settings for devices, that is 24 volts or 36 volts, like that. We are 9 volts, 2 volts, like that. Power availability, power voltage regulation, safety standard and power surgeons. So these are the considerations. And sometimes just we may get the low power, we may get the high power, power fluctuation that can be removed by voltage regulations. Next, energy harvesting in terms of solar power, thermal energy, kinetic energy and considerations. What are the considerations? Solar power, sunlight into electricity, thermal, heat into electricity, converts motion into electricity, kinetic. So energy output, environmental conditions, storage capacity, efficient. Environmental conditions, nothing but more sunlight is required. Sunlight is required for solar power. Like that, just we have to understand these concepts, considerations. Next one, factors affecting the power supply choice: device power consumption, operating environment, battery life, safety, cost and reliability. So these are the some factors affecting the power supply choice. Device power consumption, whether the device is consume low power or high power, just you can identify, you can define the before the installation. Operating environment, whether the temperature is high, whether the temperature is high, like that only, just you have to test. Battery life, whether the battery life is more or less, just that can also define. And safety, ensure compliance with the relevant safety standard, that is regulations. And cost, balance in the initial cost of the power supply with the long term operational expenses. Choose a power supply with a proven track record and suitable performance characteristics. So these are the some factors affecting the power supply choice. Next one, additional considerations: power regulation, power efficiency, battery management system, power over the Ethernet, PoE. It is very very important. Power regulation, some devices require regulated power supply for optimal operation. Power efficiency, consider the power consumption efficiency to minimize energy power consumption. Management system, battery powered devices, BMS can improve the battery life and safety. Just you can manage the whether the battery is long time work or short time work. Then it can decide by the battery management, that is DBS. And power over Ethernet can be used to power devices through the Ethernet cables only. By carefully evaluating these factors, considering the specific needs of your IoT applications, you can select the most suitable power supply option on the IoT devices. Next one, environmental factors are environmental factors like temperature and humidity. In terms of temperature, it can affect to the devices, components, battery life, sensor accuracy. Consider temperature ranges that device withstand, user enclosures or thermal management solutions if necessary. Humidity, high humidity use cases correction, select devices with appropriate humidity ratings, utilize moisture resistant enclosures. Temperature, in terms of temperature and humidity. Environmental factors, dust and particles, electromagnetic interface, vibration and stops. Physical impacts can damage components. Use shock absorbed materials, secure device purpose. In terms of dust, contaminants can clog sensors, vent and moving parts. Uses enclosures with power filtration, regular clean devices. Electromagnetic interface also, EMI signals can occur. Shield device can use shielded cables. Locate devices away from the potential EMI variation and of stacks. In terms of attitude, just we may have mitigation strategies, enclosures, material selection, sealing, ventilation, shielding, regular maintenance. In terms of altitude, in terms of security and privacy consideration also, just we may use. In terms of device authentication, data encryption, secure boot, firmware updates, access control, physical security, and network security. Privacy consideration, data minimization, data anonymization, consent management, data retention, privacy by design, transparency. Specific challenges: IoT device vulnerabilities, data privacy, network security, and data user education. So these are the security standards. Mitigation strategies also: security standards, regular security audits, instant response plan, user awareness, impact, privacy impact plan. So these are the some mitigation strategies in order to implement the IoT device. So these are the security privacy measures you can protect IoT system, your data, and build trust with the customers. So these are the main important factors we need to maintain IoT, implement IoT device on the various factors. These are the references I use for this lecture. Remaining continue with the next lecture. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.